Okay, just a few more LTL properties from our cake pie apple house, because the last ones I did in the last video, some were a bit simple, so I thought I'd just do 4 more, and if these still aren't explaining everything properly, then give me an email and I'll try and do some more, maybe bigger state transition diagram, answer any specific questions. Okay, so let's consider this one. Always, if I eat a cake, then in the next room I eat an apple. Okay, so first thing, let's find one path when this is true. XZ. Yep. Sorry. It's an always, so it has to be an infinite path. Yeah, because the reason it has to be an infinite path to make it true is because we're saying forever this is the case. Well, if you only give a finite path, then there might be some point in the future, which you haven't specified, where this isn't true. So to make this is a safety property because it's got an always at the front. To make a safety property true, you need an infinite path because you need to know what happens forever, because this says forever. Yep. So so S1, S2, S3, S4, S3, S4, S3, S4, alternating between those two forever makes this true. Yep. Because it's true in S3, X is true in S3, and then Z is true in S4. Yep. Okay, so let's consider all paths. Well, there aren't many paths in this state transition diagram. The other one goes S1, S2, S4 forever. Now, does this make this true? Yes. We have X, then Z, as specified, and then X is never true again. Yep. And then the only other paths are any kind of alternation of these two, but we see if we ever enter S3, we have to enter S4 on the next state. Yep. So any path which contains S3 has S4 straight after it, which satisfies this condition. So it's always the case that if we eat a cake, then in the next room we eat an apple. Okay, so the next one, eventually X until always Z. Okay, so let's look at one path, this one here. So, sorry, here where we go S1, S2, S4 forever. Yep. So eventually X is true here because X is true here. In S2, eventually X is not true because in S4 forever we don't have an X. Yep. So they can do the first bit. Sorry, X. Eventually X fails, which means we need always Z to be true. But Z is true there, and Z is true there. So always Z holds at S2. Note that we've replaced the pie in S2 with an apple from last time's, which threw me for a second. Yeah, so S1, S2, S4 forever holds. So we're happy. Okay. So does it hold for all paths? Well, let's consider. The case where we go S1, S2, S3, S4, S3, S4, S4 alternate forever. Yep. Well, eventually X holds throughout the entire path, but always X, always Z never holds, which for this until operator to be true, always Z needs to hold within a finite amount of time. So, in fact, if we have A until B and always not B, this can never be true. Yeah, so that can't hold. Yeah, I could write that more succinctly. Okay, so this one is false. Y implies always X. Okay, well, Y is not true in the first state, and so this is true, trivially, on every path. Yep. Now the next one, eventually y implies, on the next state, x. Yep. Now, let's try and find a path where this is true. Well, the only path where this y holds is S3, and x isn't true in S4, which means there is no path where this can hold. But to give an example of a path which breaks this, so to give an example of one path which breaks this, we'd have S1, S2, S3, S4, S4, so S4 forever. Yep. And we need an infinite path to show that this doesn't hold, because if we only give a finite path, then we don't know about the future. It might hold in the future. Yep. So we can look at the state transition diagram, we know it doesn't, but paths are our models for our LTL formulas. Yep. So we need to give an infinite path to show that, so our interpretations, to show that this formula is false in that interpretation. Okay, so that was all a bit scatty. I hope that helped a bit. If it didn't, please drop me an email. Okay, thanks.